Hi everyone. My name is Honglu Zhou, and today mostly first part I'll just give you a talk, and the topic of the talk today is intelligent video understanding through relational and compositional reasoning. So that might take an hour and a half maybe, and after that we will take a little break, and then I guess all of you have some projects like group project, right? So each group need to come here to present their own projects and just share with the rest of the audience. So if I'm correct, the class should end at 3:10. Is that right? Okay. Okay, so let's begin. So first, self-introduction. So I'm currently a PhD student from computer science department at Rutgers University since 2017, fourth semester. And my advisor is Professor Mubashir Kapadia. So my research interest mainly lie in computer vision and deep learning, especially machine learning and the reasoning that enable a deeper understanding of the semantics of the data. And the data can be in forms of video, image, graphs, human skeleton, and many more. So that's basically my research interest. And I've done many projects. For example, human group activity recognition from videos, multimodal scene boundary detection in long videos, spatial temporal reasoning. So today I will mostly introduce the first and the third project, human group activity recognition and spatial temporal reasoning. In addition, I've also done projects to like predict the human crowd behavior, and in addition to enable the intelligent and automatic floor plan design and to forecast the information diffusion, information spread, and so on. Yeah, so yeah, my current research is mostly focusing on enabling deep neural networks with relational and compositional reasoning capabilities to enrich a higher level of video understanding, computational video understanding. So that's my current research, and that's also the main topic today. And maybe you already knew about this. So our lab is called Intelligent Visual Interfaces Lab. And our research lies at the intersection of artificial intelligence, visual computing, and human-computer interaction with a mission to develop intelligent visual interfaces for human-guided content creation. And these are 4 example projects. You can find it in our website. So I guess Professor Kapadia already mentioned these to you before, so I'll just skip it. So if you're interested, you can check out the lab website, and you can also contact Professor Kapadia for more information. Okay, so the main topic of the talk today is video intelligence. And you may have known that computer vision has achieved immense success in recent years, right? However, currently, the mainstream success of computer vision are actually about the static world, with a strong focus on objects, things, and their properties. And such image-based computer vision tasks include like face detection, and the second one is basically human key point detection, and the third one is face recognition. So not only detect the face, you also need to recognize who this person is, basically. And this one is basically object recognition, and this one is scene semantic segmentation. So those are focused on the image data, and the focus is on finding out the properties of the objects and the things, right? So if a picture like says more than 1,000 words, then what does a video tell you then? In reality, a lot of more. So let's right now focus on the first image here. So it seems that in this image, this man is just sitting in the chair, and maybe he's in a very good mood, and or maybe someone said something funny, so that's why he's smiling. So everything seems to be very normal. We just look at the first image, but let's play the video. So now we know that this is actually a funny video clip. not as simple as what we thought earlier. And we might need more context to know what's really happening like in that video, right? And now let's look at the second image. Now I have a question for you. So is this girl like sitting down or standing up? Standing up? Actually, you're right. So this girl is standing up. But actually, just from the image earlier, it's hard to tell. So someone may say it's actually like sitting down. It's possible, right? So yeah, now let's look at the third image. So the question is, are they going to shake hands or high five? Oh yeah, so now it's ambiguous, right? It's actually high five. Let's see. So it seems that they are going to shake hands, but then it turns out to be high five. So because of the extra temporal information, so videos do a much better job than images in terms of disambiguating information. So that's the interesting thing, and also the challenge of modeling video data. And nowadays, producing video content with like decent production value and quality is easier than ever before. And thanks to the popularity of YouTube, TikTok, Netflix, and many other like websites, consuming video content has become a very, very common thing in our everyday life. And every day, more and more videos, either short or long, are becoming available. So it is no surprising that video understanding becomes one of the most crucial topics in computer vision. And this is a remark from CVPR 2021 tutorial on video modeling. It says, many times when we think about the visual intelligence, the key abilities that come to mind are abilities to perceive objects under properties. But in addition to perceiving the presence of objects, our experience as humans is deeply shaped by our perception of what happens to those objects. And it is really the actions, what happens to those objects, and the events that take place, what constitutes our experience and what becomes our memory. So I like this insight a lot. So our experience as humans is deeply shaped by our perception of what happens to the objects in the scene. So in this talk, when I say objects, it's more like an abstract concept. So objects are basically semantic concepts in the scene, and it includes humans. Let's look at this video to explain this point. Right. So in this video, we can see that there are like multiple persons and objects. Like the objects can be like the cake and the candles and the plates holding by these adults, and maybe pictures and photos on the wall. But after watching the video, what we really remember from it is actually not those objects, not those static objects, but actually the warm moments recorded, the event that maybe this boy in green shirt is having birthday, and maybe this is his friends or his little brother who wanted to blow out the candle for this birthday boy, and this adult wanted to prevent that, so he was holding this plate to prevent that, and also teasing with this little child. So eventually, this little boy cried, but everyone else was very happy and found it very funny. So that's what we really remembered from this video. And clearly, it's not about our perception of the objects themselves. At least it's not only about our perception of objects themselves, but these moments becomes memorable for us because of the events that happen. So really, event understanding is the key for creative moments. And events are important in memorable moments, but also our everyday life. So as said by Dr. Juan Carlos Libles, event perception changes our expectation of the future. It shapes our planning and it shapes our behavior. And to achieve event understanding in videos, perceiving the objects And not only that, understanding the dynamics and interactions of objects is very important. So achieving event understanding, it means that we need to attain a higher level knowledge for machines to have video intelligence. And this actually requires perceiving the objects as the first step and understanding the dynamics and interactions of objects as an important second step. For example, to understand what they are doing in this video and the interactions between the kids and the toy can be very useful cues. Hence, rather than building a machine that attempts to attain visual intelligence just directly from the static and low-level pixels of images, we might need to accomplish the non-trivial higher-level visual understanding from object-centric learning of videos. And it means that it might be a lot more beneficial if we just let the model to learn from features of objects instead of just image pixels. And it might be something very good to let the model to learn dynamics and interactions of the objects in order to accomplish some complex video understanding tasks that require some form of higher level understanding. So that's the key idea. So we might need to achieve higher level video understanding from the object-centric learning of videos. And among a few critical directions for visual perception and machine intelligence, reasoning, particularly relational reasoning, that reasons the synergy of objects and their dynamic interactions, and compositional learning, where we compose and decompose symbolic objects in order to form holistic representations, can help us develop robust and generalizable systems that can not only visually perceive, but also understand and even interact with the world. So therefore, we are interested in relational reasoning and compositional learning of videos. Both are ways of object-centric learning of videos. And in today's talk, I'll mainly discuss relational reasoning and compositional learning in video understanding. So before diving into more details of relational and compositional reasoning, let's briefly talk about a more general concept, machine reasoning. So the first question we might ask is why we need machine reasoning, given that we now have very matured machine learning technologies. So what's the difference between machine learning and machine reasoning? This is something called DIKW pyramid. It is also referred as the wisdom hierarchy. And according to this hierarchy, information is defined in terms of data, knowledge is defined in terms of information, and the wisdom is defined in terms of knowledge. And this bottom-up path sort of reflects the path of current AI development as well. And because wisdom is built on top of the knowledge, so to achieve the real intelligence, the machine needs to be able to manipulate the knowledge in order to gain wisdom. And the process of manipulating knowledge for humans is basically the process of reasoning. So our current neural networks, machine learning systems, have truly made success on a variety of tasks. For example, machine translation, speech recognition, computer vision, and so on. And they have been really pushed with surprising success to other tasks, which you might think that would involve higher level reasoning and understanding, such as question answering, this kind of task. But in some sense, many of our current systems have approached things as a stimulus response task that basically you provide, here's the input, and could you provide the output as a kind of statistical association task. And this kind of tasks don't really require deliberate thinking or reasoning. So sophisticated tasks require knowledge, reasoning, and inference. Hence, researchers and scientists are asking themselves, how can we develop systems that are much more intelligent than many of our current systems, and what we can do about reasoning. And because the current machine learning systems are mostly just a statistical association machine, they can be easily fooled by something called sim biases. So like, here's a question. Can you guess what action the block person is doing in the 4 videos? So basically, even though we cannot really see a human actor in these 4 cases, but it seems to be very easy for us to predict the action by just considering where the action happens. And training a convolutional neural network model from these examples may lead to a strong bias towards recognizing the scene or the objects presenting the scene, as opposed to pay attention to the actual action that the person is doing. So this is something called sim bias. And similarly here, even though we cannot really see a human actor, and we can easily predict the action by just considering what the background thing is. And however, this prediction, like swimming, might be totally wrong. So at this conference, Europe 19, there is a paper called "Why Can I Dance in the Mall? Learning to Mitigate the Sim Bias in Action Recognition." And the idea of the paper is that in a mall, the human action is not necessary to be like shopping, queuing, or whatever. So some real action like dancing can happen in the mall, right? So, however, the current new machine learning system can be easily fooled by this kind of sim bias because they're just a simple statistical association machine by learning the mapping between the input and output. And also, as a statistical association machine, current machine learning systems can be easily fooled by something called contextual biases. Here, the context means that it can either be a co-occurrence of objects and scene. For example, a boat is often present in outdoor waters. So that's the co-occurrence between boat and outdoor waters. Or it can be 2 or more objects in a given scene. For example, skis often co-occurs with a skier. So that's something called context. And existing models often leverage this kind of co-occurrences between objects and their context to improve their recognition accuracy. However, strongly relying on context risk a model's generalization ability. Another example, this is a clip in the coin dataset. And this is a video dataset consisted by many instructional videos from YouTube. However, a model can actually predict the action label replace donor by simply recognizing this donor without paying attention to the actor or any temporal changes. And this is because that the donor is only associated with action label replace donor in this dataset. So this is basically the dataset biases with respect to the frequency of labels. So how many of you have like heard of GPT-3? Like, okay. Oh, okay, I guess like at least five persons. So that's good news. So you may all have heard of like GPT-3, which is a powerful model created by OpenAI. And despite that, GPT-3 is a powerful language model that basically uses deep learning to produce human-like text. But GPT-3 sometimes behave in surprising and worrisome ways. And the GPT-3 makes simple errors that no human would ever make. For example, if you ask GPT-3 the question, which is larger, a small elephant or a large potato, GPT-3 will tell you that a small elephant is smaller than a large potato. And if you ask the GPT-3, please rank these in order from largest to smallest, a diamond ring, a tomato, an ant, a chair. And the GPT-3 will tell you that from largest to smallest, they are a diamond ring, a tomato, an ant, a chair. And if you ask GPT-3, if John has 5 apples and he gives 3 apples to Jen, how many apples will he have left? GPT-3 will say that he will only have 6 apples. And how many eyes does a cat have? GPT-3 will tell you that a cat has 5 eyes. And if you ask GPT-3, what's the result of 36 plus 477? GPT-3 will answer 5,677. So basically, GPT-3 cannot do any math problems either. Yeah, so those are some interesting results produced by GPT-3. But actually, sometimes it can be something very worrisome. So researchers have found that black box model can be hard to control, and they may hallucinate or be error prone. So hallucination is a phenomenon in natural language processing. It refers to that the problem that the generated text often contain information that is irrelevant or contradicted with input. So that's called hallucination. Those are the current very serious problems of current NLP, and something worth to think about. Moreover, current machine learning models strongly depend on large amounts of training data and supervision. And this is basically a summary of the current issues of machine learning systems. Overall, we are still building powerful neural association machines rather than a device that can think. And most neural networks are essentially very large correlation engines that will hone in any statistical potentially superior pattern that allows them to model the observed data more accurately. And current successful models tend to acquire only superficial understandings, exploiting the dataset biases rather than capturing a sound perception and the reasoning process that will lead to the correct answer. And we need a model that can flexibly deploy knowledge and can compositionally reason. And the current systems often limited in interpretability, robustness, versatility, modularity, soundness, and generalization, with requirements of large and diverse training data. So the idea is that we are still building powerful neural association machines rather than a device that can think. And we are still building a bespoke model for a particular task, and not a model which can use knowledge to reason in flexible ways. So we need a model that can flexibly deploy knowledge and reason. Otherwise, AI systems cannot adapt to our real world, which is constantly changing. So now I want to recommend this article called From Machine Learning to Machine Reasoning. The author is Leo Botto. The article was written in 2014. And in this article, he gave the definition of machine reasoning. According to him, machine reasoning is basically algebraically manipulating previous acquired knowledge in order to answer a new question. And enriching this algebraic structure then leads to the higher forms of reasoning. Machine learning is, on the other hand, more related to the statistical nature, correlation. And let's think about human reasoning. So for humans, when we observe a visual scene or when we hear a complex sentence, we can explain in formal terms the relation of the objects in the scene or the precise meaning of the sentence components. So we can understand the visual scene or the complex sentence by manipulating our knowledge of those scene or sentence components. Humans are basically subconsciously performing reasoning all the time. So even though in both of the images, a person is having an accident with a scooter, but based upon the fact that there are other moving objects in the left image, such as like a moving car and other pedestrians and the man riding on the bicycle, So whereas in the right image, the person who is falling is actually on the sidewalk, and the street is quite empty. So it is easy for us to recognize that the first situation, the left-hand side situation, is not safe for the traffic, but the right-hand side situation might be safe for the public. So what I just described is basically a potential reasoning process that a human would do. So basically start off with recognizing all the objects, figuring out the precise meaning of the objects, and then reasoning the relations of objects, finally arriving at a conclusion based upon those existing knowledge. So the challenge is actually how can reasoning, which has traditionally been thought of in connection with logics and hand-built knowledge representations, be learned by deep learning. And this researcher, Christopher Manning, said that traditionally reasoning has been the domain of logics and hand-built knowledge representation, but maybe we can think about how we could use the distributed representations learned by neural networks as a way of reasoning. And he suggested that building the right kinds of inductive biases, such as structure bias, into the models can help model to learn quickly and well. And the way to basically the way to build something called composition rules for multi-step reasoning in the neural networks. And the examples of the structure bias can be convolution, gating in LSTMs, and the attention mechanisms. So if you are interested in this kind of topic, you can basically check out these videos or search inductive biases, machine reasoning. Yeah. Okay, so we just had a small deviation from the main topic of the talk today. And we just discussed the machine reasoning at a high level. So my goal was just to help you to know that the issue of the current machine learning and how machine reasoning differs from machine learning, those basic high-level concepts. And yeah, machine reasoning is one of the most important directions in artificial intelligence because it really has inspired me a lot in my research. So I hope it can also inspire in some certain ways. And now I'm going to talk about the main two topics, relational reasoning and the compositional learning in video intelligence. So intelligent video systems with the capability of relational reasoning usually reason the saliency of objects and their dynamic interactions. So for example, in this video that we just played, we may identify the cake and the plate and the adults and the kid who cried in the end as the most salient objects. Again, when I say objects, it's basically the concept includes persons. And we may also find the interactions between the adult and the kids, the interaction between the adult and the plate, the interaction between the kid and the cake are the crucial dynamic interactions. So a model with a capability of relational reasoning should do the same thing. It should learn and reason the saliency of objects and their dynamic interactions. And relational reasoning has many applications, and it is usually the key component of current machine reasoning systems. For example, autonomous driving. So as humans, when we are driving, we would basically recognize like the traffic lights, the road signs, and maybe the pedestrians and other cars. And then we would form an understanding of relations between them. We would decide on how to navigate based upon the reasoning process, because instead of just detecting those pedestrians, cars, and so on, we must reason the meaning behind the static objects, how the pedestrians and the cars move, and predict where they will move. So we must reason the objects themselves and the dynamic interactions of the objects. So that's basically relational reasoning. And the relational reasoning is also performed when a human watches this security camera footage to decide whether the person in the video is stealing packages or making a delivery. So in the case of making a delivery, the dynamic relationship between the person and the package might be putting down. And whereas in the case of stealing the package, the relationship between the person and the package might be picking up. So we have tons of real-world applications of reasoning, apart from self-driving and home safety that I just described. Other applications could be AR, VR, public safety, video analytics and organization, robotic manipulation, and retail intelligence. So our group has worked on relational reasoning for video understanding. And next, I'll introduce our proposed solution, Hopper, which is a framework. And this Hopper framework was designed for the task of video spatial temporal reasoning. And the task here is video spatial temporal reasoning. Let's consider detecting shoplifting given a video footage. So the person in the video might just walk around, then hold an item, and then maybe he or she would put the item into the pocket and finally walk out of the store, right? So that might be the process of shoplifting. And it is actually not non-trivial for any model to know that the person has the item in the end of the video because it's hidden, right? So for a model to, and this actually means that video understanding requires spatial temporal reasoning. And for a model to detect shoplifting, first, the model needs to recognize person and items. Second, the model needs to recognize the atomic actions of the person, such as walking around, holding an item, putting an item into pocket, and walking out of the store. And the third, the model needs to recognize the temporal order and then reason about the importance and the relations between these actions. And the problem involves a concept called object permanence. Object permanence is basically the ability to represent the existence and the trajectory of hidden moving objects. And the object permanence can be essential in understanding videos in activities such as shopping. One basically is to infer what item the shopper should be built for, or driving, basically to infer if there are a pedestrian in front of the car who's going to pass the streets, and other cases, right? So answering these questions require the ability to predict the location of non-visible objects as they are occluded, content or carried by other objects. So hence solving the task requires compositional multi-step spatial temporal reasoning. And now let's watch a video. So this is called cup and ball shell game. I guess you know about this. So apparently humans and even cats can solve this type of long temporal reasoning tasks. But this is definitely a very smart cat. My cat cannot do this. And inspired by this game, researchers decided to design similar hard tasks for computer vision systems. So at this conference, iClear 2020, a synthetic data set called Cater was released. And this Cater data set is a diagnostic data set for systematic evaluation of video models. So what does it mean by saying diagnostic data set? So in those kind of data sets, it's usually synthetic data sets. And we mentioned earlier that machine learning model often exploit those data set biases to have a very good accuracy, right? So researchers design those kind of diagnostic data set by controlling any potential data set biases that the model may exploit. And so that's why it's called diagnostic data set. It can assess the true ability of the models. And in this K-12 data set, every video basically has a special object, which is a small metal like object, golden object called snitch. And there are usually multiple objects in the video, and those objects can be in different colors, different shapes, different sizes, and those objects are afforded with different actions. So the objects can be sliding along the table plan, and it may rotate, and it can also be like picked up into the air along the y-axis, and then it can move to a new position. And if the object that was being picked up is actually a cone, and this cone can contain another smaller objects, so that smaller objects will be inside of the cone, will be covered by the cone. And since the cone can keep moving, so the location of the object inside the cone will be changed. So that's the basic dynamics of the objects in this data set. And in this data set, there is a task called snitch localization. It means that we basically need to find out where the snitch is in the end of the video. So for example, we can see that our friend 10 snitch is here, friend 11 snitch is here, and at friend 12, basically, I think this cyan cone covered the snitch. And at frame 13, this cyan cone moved a little bit. So the researchers who released the data set has turned this table plan into 6x6 grids. So basically need to find out which grid contains the snitch in the end of the video. So that's why it's a classification task for snitch localization. So the task will basically need to find out where the snitch is in the end of the video. And because of the different actions of objects, so this task actually implicitly requires non-trivial spatial temporal understanding and the multi-step long-term compositional reasoning. And we propose a framework called Hopper to address the task. These are 4 key ideas. First, object-centric learning. Basically, the idea is that humans would usually think in terms of entities and the relations between them. So when we design this framework, the key idea is to leverage object-centric learning, object-centric relational reasoning. And that's why in this Hopper framework, illustrated here, we start with an image backbone to obtain the features of each frame. And then after that, it's the object detection module. This object detector will basically detect the location of all objects in each frame. And it will also tell us the class label of the object, and also it will give us a high dimensional representation vector of each object. And then we also think that tracking can be beneficial because tracking can aggregate sequence features in time order and give consistent feature representation. Basically, tracking links the same objects across time. So that basically can help the model to understand the dynamics of the objects. So the third module of the framework is basically a tracking module. And the key novelty part of this Hopper framework is the last module, which is based on multi-step compositional reasoning. And the intuition when we designed this multi-hop transformer to perform this multi-step compositional reasoning is that humans would usually think in steps and understand the world as a sum of its parts. So like when humans try to solve the snitch localization task, we might need to first identify like the last visible snitch. And then we basically will focus on the container or occluder of the last visible snitch. So we basically solve this snitch localization task in a step-by-step manner. So yeah, and there are other novelty parts. For example, we, as I mentioned earlier, machine learning systems often suffer from leveraging superior dataset biases. So we design a loss term to do contrastive debiasing. Basically, the key idea of that loss term is to make sure that the model should not be able to make the correct prediction without seeing the correct evidence. Yeah. Right. So this basically illustrates the how the multi-hop transformer performs reasoning by hopping over frames and objects. So as I mentioned earlier, the key idea of multi-hop transformer is to perform step-by-step reasoning. So we hope that this multi-hop transformer can give us a reasoning step in each of the hop. So hop is also basically also step. So at every step, at every hop, we hope the model to give us a reasoning step. And in this example, in this test video, basically, so let's look at the frames first. So here, since we use 1 FPS, so each video has approximately 13 frames. So frame 13 is the last frame in the video. And in this video, we can basically find that the last visible snitch is actually at frame 1. And then we have this red rubber cone covered the snitch. And then after that, we have this larger cone covered the smaller red rubber cone. And it basically keeps going. In the end, the smaller red rubber cone moved a little bit. And in the end, the snitch were inside of this red rubber cone. So in the end, the location of snitch is here, inside of the red rubber cone. And we find that the reasoning step performed by the multi-hop transformer is basically at the first step, it will identify the last visible snitch, the snitch at frame 1 as the most important object in its first reasoning step. And in its second reasoning step, it identifies this red rubber cone as the most important object. And in the third reasoning step, in the third hop, the model identifies this red rubber cone at frame 10 as the most important object. And then the fourth reasoning step, hop 4, it identifies the cone at frame 12. In the end, in the last step, it identified the red rubber cone at frame 13 as the most important object. So that's the reasoning step performed by this multi-hop transformer model. and it works by performing reasoning in a hopping over frames and objects. So in this hopper framework, the structural biases such as attention here are essentially something called composition rules that provide good and bad inductive biases and lead to the higher forms of reasoning. So this multi-hop transformer is based upon transformer model, and the transformer model nowadays is very popular. It's so, for example, GPT-3 mentioned earlier was based upon the transformer model, and this multi-hop transformer model is also designed based upon transformer, and the transformer is based upon attention mechanism, and which are usually the key to perform relational reasoning. So if you are interested, I highly encourage you guys to learn more about attention and transformers. And this basically illustrates the architecture details of the, yeah. Yes. So this Hungarian is basically the name of unsupervised technology. So it's basically the name of a family of unsupervised technology. Because unsupervised means that we don't have one case of the sort of basically, even that we know the object location in the previous step, and next step is always try to find out which object located the location is most similar to the previous object location, and we want to try to find out that we try to make sure that the object in the next step that has the most location similarity with the exact object. Basically, the idea of the hazard object. Every two consecutive two flags, we try to think the object in the exact object. That's basically the idea. It's a very simple idea of abstract. And we use this way because it's very cheap. We don't have strong presentation. So here we illustrate the architecture details of the multi-hop transformer. So I'm not going to dive into more details here. The basic idea is that this multi-hop transformer operates in an iterative fashion. So it means that we will sort of apply multiple forward passes by using this module multi-hop transformer. And for example, when we apply the forward pass of this multi-hop transformer for the first time, that's basically hop 1. And the input objects to hop 1 are basically all objects in the frame. And that's something called object candidates. And given all these object candidates, this multi-hop transformer needs to identify the last visible snitch as the most important object in its first step. And that's ensured by a training loss. So we want to make sure that the first step, the model will identify the last visible snitch. And after identifying the last visible snitch, because if the last visible snitch is not in the last frame, it means that we haven't really find out where the snitch is for the snitch localization task, because the task asks you to find out where the snitch is in the end of the video. So in that case, that means the model needs to perform a second round of reasoning. So then we'll basically apply this module, we'll do the forward pass for second time. And that's basically hop 2. And at hop 2, the object candidates becomes into the object representations after the frame where the last visible snitch is. For example, here, the last visible snitch is at frame 12. So that means at the second hop, all the objects after frame 12 becomes into the candidates for the model to further decide on where the final snitch is. So in this way, maybe the second hop, the model will identify this green cylinder as the most important object. And because the green cylinder at frame 13 is already the last frame, that basically means that the model should stop from reasoning. So that's the idea of the multi-hop transformer. It operates in an iterative fashion, and each iteration, each forward runs, it will produce a reasoning step. And another very good thing about using transformer models and attention is that it can give us some qualitative analysis. It can basically, we can identify something called attention weights, and this attention weights will tell you that which object, which entity that the model thinks is the most important for the task. So we can visualize the attention weights, and this basically tells us how the model thinks in order to solve these tasks. And in this first qualitative result, basically, in the end of the video, the snitch is visible. He's here. So we find that our model basically performed the one hop reasoning, and at hop 1, it identifies this snitch as the most important objects by visualizing the attention weights. And in this second example, so the snitch is last visible at frame 12, and then this green cylinder moves and occluded the snitch. So in this case, we found that the model performed 2 steps of reasoning. The first step, the model identified the snitch at 12 frame 12 has the most important object. And at the second step, the snitch identified the green cylinder as the most important object. And there are more examples. This is a case of containment. So basically, the snitch was last visible at frame 9, and then occluded by it was contained by the green cone, and in the end, it's just the inside of the green cone. And so at hop 1, the model identified this snitch. Hop 2, the model identified the green cone, and hop 3, 4, 5, it keeps paying attention to this green cone. And this is a case of recursive containment. So in this video, basically last visible snitch is at frame 9, and then this red cone covers the snitch, and then at frame 12, this yellow cone covers the red cone. So this is called recursive containment. And again, our models gives us some very reasonably multi-step reasoning process. And in this case, the snitch becomes not visible very early. So the last visible snitch is actually at frame 1. So at the second frame, the snitch becomes not visible because this the red rubber cone covers the snitch. So even for this kind of cases, our model can perform a reasonable reasoning. And there is some issue with the Cater dataset actually. We found that basically in the dataset of Cater, like almost 60% of the videos have the snitch visible in the last frame. And there are almost 15% of videos have the snitch visible in the second last frame. So here it basically means that there are almost 75% of videos have the snitch last visible in the last 2 frames. So as I mentioned earlier, the Cater dataset was supposed to assess whether the model has ability to perform long-term reasoning. But if like 70% of video has the snitch visible in the end, then it's not a difficult task at all. It cannot really assess the model's ability to perform long-term reasoning. So that's actually, it actually means that the original Cater dataset has the temporal biases. So So we correct this issue by releasing a new dataset called Cater Hard. So Cater Hard is the same as Cater, except that we make sure that every frame index has the equal number of clips to have slits visible in that frame index. So we will basically reduce the temporal biases in the original Cater dataset. And this table is basically the quantitative results. So the metrics are top one accuracy and L1 distance. Because it's a snitch localization task, so we can use L1 as a metric. As you can see here, our proposed multi-hop spatial temporal reasoning model Hopper outperformed the SOTA techniques by a lot. In addition, as you can see that this Cater Hard dataset is much more difficult. It's much more challenging for the existing models to solve. So that the top one accuracy of Cater Hard is much lower than the top one accuracy of Cater. So another good thing about using attention-based model is that you can visualize the attention weights and you can examine those failure cases. And this is an example of failure case. So in this video, the snitch is contained by the brown cone here, basically at frame 5. So the last visible snitch is at frame 4, and then this brown cone covers the snitch at frame 5, and then this brown cone moves to the back of the cube at frame 6. And after that, the snitch is behind of the cube until the end. And for this case, our model kind of identify that the snitch is inside of this CM cone instead. So it basically failed to identify the correct object to pay attention to. And the second failure case, basically, the snitch was last visible at frame 2, and then this cyan cone covered the snitch. And after that, the cyan cone is contained by the yellow cone twice at frame 5 and frame 9. But in the end, the cyan cone is actually visible, and the snitch is inside of this cyan cone. But in this case, our model identifies that the snitch is inside of this yellow cone instead of the cyan cone. So those are two failure cases. And after identifying many of these failure cases, we summarize that generally a video is more difficult for Hopper if there are similar looking objects present simultaneously, especially if the object is similar to snitch or another cone in the video. And the second, if for this video, our Hopper model identified the wrong hop 1, hop 2, it is because that the hop 1 is basically the first reasoning step. If you start with a wrong first step, then basically the rest of the steps are not meaningful at all. So, and in addition, when we train the Hopper model, we want the model to identify the last visible snitch at hop 1. So hop 1 is very important. And third, if the critical moments are occluded. For example, in this failure case, when the snitch become occluded by the cube, it was actually inside of the cone. So that basically means that the critical moment of occlusion itself is actually occluded. So the critical moments, if the critical moments are occluded, then it's a very difficult video. And the fourth, if there are like complex object interactions, such as recursive containment, along with the container moving, so that's also another very difficult case. So yeah, so this slide basically summarizes our main contributions. So the main contribution is that we propose a framework of Hopper that can perform multi-hop reasoning automatically, and the Hopper framework offers interpretability. In addition, we achieved SOTA performance on cater dataset. And we also released a new dataset called cater hard that requires longer reasoning hops. And the possible future work can be, we can further apply this hopper framework to address some video language problems such as video question answering. So researchers believe that question answering is a very good task to assess whether the model has the reasoning ability or not, because like even for kids, the way to assess whether the kid is intelligent or whatever is by asking questions, right? So they are thinking that question answering should be a very good task to assess whether the model has intelligence. And in addition, we intuitively, even though we just use the hopper to solve this snitch localization task, which is based upon a synthetic data set, but intuitively, we can apply this hopper model to solve some real world problems, such as detecting shoplifting. Because the idea behind are very similar. It's all based upon the idea of learning object permanence. Yeah, so that's basically our efforts in solving relational reasoning. And next, I'm going to talk about compositional learning of videos. And maybe let's take a 10 minutes break. Yeah, 5 minutes? Yeah. Oh, yeah. You want to? Oh no, we actually sample from former. So basically, every step has like every second is one step. It doesn't matter what the back or movement. So sample is that this is another example to after movement at all. So just sample from. So why mentioning it is that maybe using one of the healthcare it wasn't very close from it, just from it. It can be possible that some dynamics one healthcare form. So we think that maybe it fits the SDS to a diagram my copy model to sample this language of the model. But that's not possible way to increase the SDS. But just make to remember that when we increase the ground, that means that we have more interest in the model. More data may be used by development from the model to identify the subtle signals from more that also so dynamic that may mean that we also increase the FPS so let's take a 10 minutes break. Thank you so much. Okay, let's go back to our lecture. So the next part of the topic will be about compositional learning. The ability to compose and decompose symbolic objects is basically one of the most marvelous feats of the human mind. And according to Jerry Fodor's language of thought hypothesis, thinking itself possesses a compositional structure where elementary concepts combine in systematic ways to create compound new ideas or thoughts, allowing us to make infinite use of finite means and fostering humans' remarkable capabilities of abstraction and generalization. So indeed, humans are particularly adept at making abstractions of various kinds. We see things in context and build compositional models to represent objects in different levels of hierarchies and understand their interactions and subtle relations, turning raw sensory signals into high-level semantic knowledge. And the emergence of ideas about compositionality, abstraction, and reasoning has greatly advanced artificial intelligence. Compositional learning, computer vision, natural language processing, or machine reasoning basically means that we hope the model to form holistic representations or understanding through composing or decomposing symbolic objects. And for me, I'm particularly interested in compositionality in human-centered videos. And drawing from cognitive science studies, a hierarchy of human actions can either be taxonomic, for example, playing basketball is a kind of sport, or patronomic. It basically, an example is that take an order is a step of dining service. So there are these two different angles of compositionality, taxonomic or patronomic of human action. And for patronomic, this angle, we can also like decompose the human action in a spatial scale or in the temporal scale. And in terms of understanding videos centered on human actions, compositionality can be studied from different lenses, for example, spatially, temporally, or taxonomically. And this is a dataset called COIN, and it's a compositional learning dataset example. So in this COIN dataset, the videos are from different possible domains. For example, it can be from vehicle domain or household domain. And for each of the domain, there might be different tasks. For example, for the vehicle domain, changing the car tire might be one potential task. And for each of the tasks, for example, changing the car tire, it usually has multiple steps to complete this kind of task. So for this COIN dataset, basically, the kind of divide the video in both like taxonomical way or like in a temporal way. And this is another dataset example called MoMA. And in this dataset, they have considered to decompose an activity, for example, dining service, into several sub-activities, such as taking the order, serve food, and clean up the table. And for sub-activities such as serve food, it can be further decomposed into several atomic actions. For example, here, maybe we have like two customers talking to each other, and for the waiter, maybe the waiter is talking, holding a plate, or putting down a plate. So different atomic actions. And further, we can also even decompose atomic actions into basically more fine-grained interaction level thing. It's called scene graph action hypergraph. So it's more fine-grained. It's based on the interaction of objects in each frame. And this is another dataset example called 5G. And in this dataset, basically, we can temporarily decompose events into several things. They call it as sets, and for each of the steps, it can also be further decomposed. And this is another example called multi-supports. And in this data set, there are basically 4 types of support. It can be gymnastics, basketball, football, or volleyball. And in each of the sport type, there might be different activities. And some researchers would also further decompose actions by action-based aspects and object components as a series of dynamic human-object interactions. So one famous example is called action genome. And this is another example called something else. For example, for the first video, the label is moving marker and marker away from each other. And for the second video, the label is moving the cup and glass away from each other. So for these cases, they're focusing on the more fine-grained interaction level compositions of their actions. And one thing to note that the idea of multi-scale learning has been a long-standing topic in computer vision. And so compositional learning is not a new concept in computer vision. And basically, multi-scale representation learning is implicitly performing compositional learning. So, and for example, this figure is taken from this false reference. Dynamic multi-scale graph neural networks for 3D skeleton-based human motion prediction. The idea is that they consider a human skeleton from different scales, so multiple scales, and each scale, it kind of like the scale 3 is kind of an abstraction of scale 2, and scale 2 is an abstraction of scale 1. And by using these different scales, basically body components represented in different scales, they can better understand the human motion dynamics. They can learn better representations of those body components. So that's the idea of using multi-scale learning, multi-scale representation learning to enable the better accuracy of the downstream tasks. And the idea of multi-scale representation is basically implicitly the compositional learning. And we also studied the compositional learning, and we proposed a model called Composer. And as mentioned earlier, this time we focus on human-centered videos. In human-centered videos, action recognition is actually one of the primary tasks in video understanding that involves humans. And there has been rapid progress in recent years, starting from recognition of the low-level atomic actions performed by a single individual, such as surfing, hand waving, to paired actions being acted by two persons, such as hugging, shaking hands, and towards group activities that encompass many actors at once, such as pedestrian queuing, attack and defense in a sports game. Those are examples of group activities. And so here, this time we are focusing on basically the group scale, the recognizing the group activity. And the task of group activity recognition, it basically detects the activity performed by a group of actors in a short video clip. For example, the group activity of the first case is basically queuing. So we can see multiple persons queuing here. And for the second case, the group activity is talking. And by just looking at one individual, for example, this person or this person, it's very hard to classify whether this person is in a queue or whether this person is talking. However, by looking at what the surrounding people are doing, the actions can be disambiguated. And group activity recognition has widespread applications in sports analytics, civilian systems, robot-human interaction, and crowd behavior analysis. So it's a well-known task in computer vision. And the volleyball dataset and the collective activity datasets are the two commonly used group activity recognition datasets. And for this volleyball dataset, it consists of short clips of videos of different volleyball games. And each clip has one of these 8 group activity labels, basically 4 main activities: set, spike, pass, and the win point, and which are further divided into 2 subgroups, left side, or like basically left or right, because we have 2 groups for the volleyball, 2 teams. And for the collective activity dataset, it's basically a civilian video-based dataset. And the group activity labels can be waiting, queuing, walking, or talking. And in this example, it's basically people are walking. Yeah. So that's the 2 commonly used datasets for studying group activity recognition. And group activity recognition actually requires the compositional understanding and the relational reasoning. So if you think about it, the task requires the compositional understanding of the same entities and the relational reasoning between them. And first, because of the scene is usually crowded, and it's actually challenging for the model to learn meaningful representations for group activity recognition, given just the input of the pixels of the entire scene. So not just here, like in the audience, like the scene is very like crowded. So because of the crowded scene, it's very challenging for model to do group activity recognition given just the input pixels of the entire scene. And group activity often consists of 1 or more subgroups of actors and scene objects. So the final action label really depends on a compositional understanding of these entities. And in addition, group activity recognition benefits from relational reasoning over scene elements to understand the relative importance of entities and their interactions. For example, in a volleyball game, as we can see that this person is performing the setting behavior. So intuitively, this person is way more important than other players. Especially, it should be more important than those players who's just standing by. So basically, the importance of our entities in the scene is usually non-equal. That basically means that we might need to perform some relational reasoning to identify those salient entities, and also to understand the interactions between those entities. And inspired from this, we basically propose a model called Composer by leveraging compositional learning and the relational learning for group activity recognition. And yeah, this is the basic ideas of Composer. We propose a Composer for group activity recognition by modeling a video as a series of tokens that represent the multi-scale semantic concepts in the video. And the multi-scale semantic concepts include the human key points and the person scale and the person-to-person interactions, person group, and object if present. For example, in the case of volleyball, the ball is an important object, and overall, the course scale concept is the overall clip. So we have these different multi-scale concepts, and in addition, we can sort of form a hierarchy by linking the actor-related concepts. So the finance scale is basically the key point scale. Key point basically means like the joint of the person, such as wrist, ankle, those kind of things. So the finance scale, the actor-related scale is the key point, and by combining the key points of one person, we basically have the concept of the person scale. And by combining the interaction of every 2 persons, we basically have a 3rd scale, which is the interaction scale. And by combining the person that belongs to one group, one team, we basically has a 4th scale, which is the group scale. So that's how we design these 4 different scales from the most flagrant level to the courses level. And of course, at each scale, we can have a representation of the objects and a representation of the clip. The idea is that if I just give you the information of entities at one particular scale, such as the key point scale, but just providing you all the representation of key points and also representation of objects, it is possible for you to recognize the group activity given just the key points. And similarly, if I don't give you other information, I just give you the representation of all the person, it is possible for you to recognize the group activity given all the person information. So meanwhile, we hope that we can have a we can have a hierarchy, but meanwhile, we hope that at each scale, our model will still be able to perform the group activity recognition. Our model still have enough information to perform group activity recognition at each scale. That's how we design these different scales for Composer. And after identifying these semantic scales, we basically from these 4 different scales, and those are the example key points. So here we consider 17 key points for each person. It can be nose, left eye, right eye, ear, shoulder, elbow, yeah, and so on. So that's the key points. And because we form this kind of hierarchy, that basically means that the representation of actor-related tokens in coarser scale can be learned and aggregated from actor-related tokens of the finer scale. It basically means that we start with the key point representation, and after the model kind of refine the representation of the key points, then we can simply aggregate all key point representation of that single person to form a representation of the person. And similarly, given 2-person representation, we can aggregate that 2 representation vectors to form an interaction representation vector. So the actor-related tokens in coarser scale can be learned and aggregated from the actor-related tokens of the finer scale. And these basic ideas basically help us to design this Composer model. And most importantly, Composer facilitates compositional learning and the relational reasoning. First, it facilitates compositional learning by sufficiently making use of the multi-scale scene elements in the group activity recognition task. Basically, the left-hand side is the Composer model, and the right-hand side is the architecture details of this multi-scale transformer block. This multi-scale transformer block, the main functionality is to perform relational reasoning over the entities. As you can see that the input to this left-hand side to the Composer are, so the CLS means that it means a classification is an overall video representation vector. And the input of this Composer includes the CLS token, the video representation, and object tokens, basically object representations, and the key point representations, person representations, and interaction representation, and the group representations. So those are the initial representations that input to the Composer model. And then these representations are input to the multi-scale transformer block. And as you can see that the outputs are basically the same thing. So the outputs from the multi-scale transformer block are the representation of the group, interaction, person, key point, and the object. So basically, the main functionality of the multi-scale transformer block is to refine the representation of those entities by performing relational reasoning between these entities. And the relational reasoning is again achieved by attention mechanism by transformer models. So basically, the compositional learning and the relational reasoning are the key ideas of Composer. And there are other novelty things such as we try to learn consistent cluster assignment across the different scales of the same clip to encourage consistent multi-scale representations. The idea is that, as we mentioned earlier, intuitively, a model can be able to perform group activity recognition given the information of one particular scale. So that basically means that at each scale, we can ask the model to predict the group activity. So basically, since we have 4 scales, our model can have 4 different video representation and to predict 4 times of group activity. And given these 4 different video representation, Yeah, question. So basically, with all these, we actually have like some key processing module which extracts the key points of each person. And let's say each person has 17 key points, and each key point has the XY coordinates and also the frequent path. So this is basic information. And then we basically use like multi-layer perceptron to change the dimensionality of the key points into a stem three-dimensional vector. Basically, we cannot combine the original basic information of the key points into a overall vector. So basically, here, like each token basically means a three-dimensional vector of a certain key point of a person. So basically, before this, there are some pre-processing modules that extracts the basic information and form the initial representation of those key points, like person or whatever. So actually, to this time, so the pre-processing module cannot aggregate the different concepts. Let's say that like there is a person and we basically aggregate that person's like ankle in all concepts as ankle track to that person. So that's one people. So basically here, so each token like key point of person, it has information, but it has a time information because before we form this three-dimensional representation for each person, we kind of already aggregated the person representation across the time. So by using like NLP or whatever. So that's the difference between the last work and the last work. Like each entity is basically the representation of the entity of people set. At this time, each entity is the representation of that entity on across the entire yeah. So here, like leveraging the two really they have like already fixed the FPS and after I don't know the example but basically using the fixed FPS it gives us turn track. So focus on short turn track. This will have 10 timestamps for and that basically means that when we form this person token, we basically aggregate those that person's representation with timestamps. So eventually the input to composer or manuscript composer is actually the person representation combined from those representation. Oh, yeah, that's possible. That is basically when the person entity appears. So the initial representation of that content will be zero vector. And then that zero vector will be combined. Yes. So sometimes it's mentioned that when we like use this model that we are assuming that we there is a one and also the Okay, I was talking about this third point, like we learn consistent multi-scale representation. The idea is that, as we mentioned earlier, we have like 4 different scales, and intuitively given information of one particular scale, our model can predict the group activity. So that means our model will have 4 different representations for the clip, and it will basically predict group activity for 4 times. And given those 4 different representations of the clip, since these are the representation of the same clip, but they're just learned at different scales. So we're hoping that these different representation of the clip can be consistent. Basically, it means that we're hoping the high-level semantic thing embedded in those representations, the high-level knowledge are the same. So in order to make sure that these multi-scale representations are consistent, we also design a loss term, which is to basically ask the model to do clustering. The idea is that we use a clustering algorithm to cluster those clip representations. So for example, we have like 4 different scales of the clip learned, like 4 different representations, and we will ask the clustering algorithm to cluster the clips, and we want to make sure that the different clip representations of the same clip will end up in the same cluster because they are from the same clip, right? So in the end, they should belong to one cluster. That's the idea. So we want to learn a consistent cluster assignment. Basically, to be more specific, let's say we have the representation of the clip learned at scale 1, and we will use that clip representation to we'll get the cluster assignment of that clip, and we'll also get a cluster assignment of given the input of the clip representation learned at scale 2, and our loss term is trying to ensure that these 2 clip representation will end up in the same cluster because they are all from the same clip. So that's the idea, how to learn consistent multi-scale representations. And moreover, here we also try to address the thin bias problem. Here, the way we address it is by just using the key points on the modality. So as I mentioned earlier, so for those models that use RGB input modality can often suffer from the thin bias by focusing on the thin background, such as the swimming pool. So, and that's usually because of using the RGB modality. So this time we try to address the thin bias problem by only using the key point modality. So the input are just the key point information. And this helps the model to be robust with related to changes in the backgrounds, lighting condition, and textures, and so on. And this table is basically the quantitative results. It compares our method with SOTA techniques that leverage only the key point information. And as you can see that our model composer outperforms the existing methods and achieves a new SOTA results. And this one basically compares our model with SOTA methods that use RGB or multiple modalities. So here post basically means the key point modality, and RGB, and the flow it means something called optical flow. It's another modality. And the thing here, it means that the model additionally use the features of all the features of the pixels of all the images, all the frames. So it uses the features of the overall thing. So from this table, we can see that our method composer, which only uses the key point modality, it outperforms the latest methods that use the RGB signals. And also it performs favorably compared with methods that exploit multiple modalities. In addition, researchers have released a skewed Olympic split of the volleyball dataset. And in this skewed Olympic split of the volleyball dataset, the training and testing videos are split according to the match venues. So basically, the training videos are all from the same 2012 London Olympic venue, and the testing videos are from different venues. So that basically causing the training data and the testing data have different scene backgrounds, as you can see here. And by using the model to see the performance on this Olympic split, we find that the RGB-based methods suffer a lot from the scene bias. So as you can see, the accuracy of RGB-based method is much lower than the accuracy of these methods on original split of the volleyball dataset. And our model Composer, it can generalize to test data with distinct background characteristics. And our model has an outstanding scene generalization capability. And because Composer also uses transformers, we can also visualize the attention width, and the model can also offer interpretability. So here, this figure A in the top right corner is the visualization of the confusion matrix on the volleyball dataset, and here the B part is basically the visualization of the attention width from the last multi-scale transformer block in Composer. So from this figure A, we can see that the Composer achieves the accuracy over 90% for each group activity class. And for B, we can see that Composer is able to attend to relevant entities across different scales. So in these visualizations, the darker color denotes larger attention widths. So for example, at the scale 1 key point scale, we found that the model is mostly pay attention to the wrists and the knees and ankles of actor 0. So this person is the actor 0 who is actually performing the setting behavior, if you look carefully. And at the second scale, we found that the model is mostly pay attention to actor 0 who is actually performing the setting behavior. And at the scale 3, person-to-person interaction scale, we find that the model is mostly pay attention to the interaction between actor 0 and actor 1. So this is actor 0 and this is actor 1. And also actor 0 to actor 2, actor 0 to actor 4, and actor 0 to actor 5. So those are identified as the most important interactions by the model. And at the fourth scale, the group scale, actually the model is mostly pay attention to the ball trajectory, to the ball information, the volleyball. So yeah. And similarly, we can check the failure cases. So it would always be very beneficial to check the failure cases. You can learn a lot from it. So in this testing video clip, we find that basically the ground truth is the right spike, but our prediction is left spike. And the reason our model give a wrong prediction is actually because the camera position differs a lot between training and testing. So even for humans, when you look at this video, you don't know whether it's left spike or right spike, right? So that's main reason different camera position between training and testing. So in the original, in the current volleyball data set, for the most of the videos, the camera position is actually fixed, and it's different than this kind of camera position. And this is a test clip from the collective activity data sets. And this time, we basically visualize the estimated key points and the tracks and also the ground truth action of each person. Yeah, so and from this visualization, we can see that because of the occlusion, the estimate key points of like person 2 and person 3 are actually very noisy. And because of the noisy estimated key points, our model made a wrong prediction. So the ground truth is queuing, but our model was predicting weighting. So our model made a wrong prediction because this Q is kind of interrupted by this person. The Q was cut off in the middle due to the occlusion. So these actually suggest the possible ways to further improve the current model. So the current model suffers a lot from noisy estimated key points, maybe improving the initial key point representation or design some techniques to address the noisy estimated key points are some interesting directions. So, okay, so the contributions of this work are basically we propose a model called Composer to leverage compositional and the relational reasoning at different scales for cooperative recognition. And even though I did not mention those technical details in a very detailed manner, we also propose some techniques to improve the intermediate representations. In addition, the model can attend to relevant information across scales and offers interpretability. And we achieved the state-of-art accuracy on both voluble and collective activity datasets. And more importantly, our method has an extraordinary scene generalization capability using only the key points input modality. And possible future works can be to expand our models to like more complex scenarios, such as the crowd understanding that may require modeling additional hierarchical scales. So according to this paper, they are saying that the levels of human activity analysis are basically 3 levels. The first level is human action and the group activity and the crowd behavior. So to model the crowd behavior, currently we are using like that 4 scales, but maybe we might need additional skills to model more complex scenarios. And we can also use additional modalities like RGB, which can be beneficial for activities that involve significant interaction with objects or the background scene. So there are cases like we cannot ignore the background scene. So in those cases, maybe we should further to use the RGB modality. Meanwhile, we need to make sure that we still have the good scene generalization ability. Okay, so now is the summary of the talk. So in the end, I just want to first is some takeaways. So suggestions if you are interested in machine reasoning. So I was really like interested in machine reasoning, and those are some things that I summarized. Basically, if you want to work on machine reasoning, you might need to work with some diagnostic data sets. And when you use this diagnostic data set, either releasing a new data set or use the one, you need to pay attention to the potential data set biases to avoid the model to use take any shortcuts. And in addition, you need to make sure that these data set can encourage the model to perform compositional reasoning. In addition, this data set better require an array of challenging reasoning skills such as temporal reasoning, causal reasoning, multi-hop reasoning, mathematical reasoning, counting, comparison, and so on. And the data set itself should be fully controlled and well annotated. And if you want to do some research in machine reasoning by proposing some improved neural network designs, then the following things are something you can think about. For example, you need to move away from the black box neural network architectures, and it's better to impose some strong structure priors into the neural network architecture to guide the network towards a compositional reasoning. And you need to avoid exploiting training data set biases, and the modular networks are common. And graph-based relational or interaction-based modeling are encouraged. And also you can design some pretext tags and self-supervision, and try to retain end-to-end differentiability and demonstrate the scalability to real-world problems. And usually machine reasoning has a lot to do with interpretability, because we want the model to have a transparent reasoning process. And I guess the slides will be available to you guys eventually. So I also collected some data sets that I found to be very, very interesting. So these slides are mostly data sets that focus on that is focusing on visual reasoning, visual machine reasoning. And there are more data sets that's which are not necessary to be related to machine reasoning. I just found them very interesting, which you can take a look if you are interested. And that's all. Thank you very much for listening.